Hi, and welcome to Project 2 of EECS 280. In this project, I'm going to be showing you guys how to do proof by contraposition. Now, let's first off start by looking at what a contrapositive is. So, if you have the statement P implies Q, then the contrapositive of that statement would be the statement not Q implies not P. And the reason why contrapositives are important is because the truth tables for contrapositives are exactly the same as the truth tables for the regular implication statement. So let's go ahead and look at those truth tables. Now you can see P implies Q, the truth table is only false when P is true and Q is false. And then the rest of the time P implies Q is true. If we look at the truth table for not Q implies not P, we can see that it's again only false in the same location. It's only false when not Q implies not P, or not Q is true and not P is false. And not Q is false, or not Q is true when Q is false, and not P is false when P is true. And so if we have here P is true and Q is false, then that is false up in this original implication statement. And the reason why this is really important is because sometimes you can't prove something by just using a direct proof P implies Q. And so what you need to do, because sometimes that will run into a dead end, so what you need to end up doing is indirect proofs. And proof by contraposition is actually a form of indirect proofs that's really, really useful. And like all indirect proofs, proof by contraposition does not start with the premise and then find the conclusion from there. It doesn't start with P and then find Q from P, because sometimes that will just lead you to a dead end. So instead it starts with not Q, and then using axioms and definitions and things that you know, it shows that from not Q, not P follows. And if you can prove that, then you know that P implies Q is also true. So let's go ahead and start with an example. And one example of this is if x times y equals n such that n is odd, an odd integer I should say, an odd integer, then x and y must both be odd. Alright, so let's go ahead and look at what we got here. We got P is this first part of the implication. P is x times y equals n such that n is an odd integer, and Q is x and y must both be odd. Alright, so you can see here, you know intuitively that this is true. If you think about it, you run through some examples through your head, then yeah, this has to be true. But you can't solve this using a direct proof, because in order to do that, you'd have to go through every single x and y possible, and that's impossible since there's an infinite amount. So one way that we can solve this is using an indirect proof, and specifically proof by contraposition, and that actually makes it a whole lot easier. So what we can do to do a proof by contraposition, we can start by looking at our not Q and not P. So not Q is the opposite of x and y must both be odd, which is either x or y must be even. Alright, it could be one or both of them. But as long as one of them are even, then it's the opposite of Q. And not P would be the opposite of that first statement, which is simply x times y equals n, such that n is an even integer. Alright, so now if we can prove not Q implies not P, then we proved that P implies Q as well. And not Q implies not P is so much easier in this case, which you'll see. So, alright, so not Q. We'll start with the premise not Q. Either x or y must be even. We'll start with just having x be even. And by the definition of even integers, we say k is some arbitrary integer and 2k must be even. And then if we have y is odd, we'll have 2j, where j is just another arbitrary integer, and 2k plus 1, which means 2j is, or sorry, 2j is an even integer, and then if you add 1 to it, it's odd. And now if we do x times y, that is 2k times 2j plus 1, which is 4kj plus 2k. And we can simplify this to saying 2 times 2kj plus k. And again, by the definition of integers, of even integers, we have 2kj plus k is some arbitrary integer. We don't know what it is. It could be even, it could be odd. But then once we multiply 2 by it, it must be even. So this is some even integer, which is what we were trying to prove, not p. So when one of these is even, when x is even and y is odd, then x times y equals an even integer. And we can see the same thing happens when they're both even. X is 2k and y is 2j. Then x times y is 4kj, which is also 2 times 2kj, which, let's say this is some arbitrary integer, 2 times that integer has to be some even integer. So when one of these is even and the other's odd, the product is an even integer, and when they're both even, it's pretty obvious that their product is also an even integer. So we've just proven that not q, if you take not q to be true, then not p follows. And so since we've proven that, then we can say that p implies q is also true because of this truth table up here. Because whenever not q implies not p is true, p implies q must also be true. So that's one example of how you use contrapositives in proof by contraposition in order to solve something that you wouldn't be able to through direct proofs. Because you can see here we wouldn't have been able to solve this p implies q using direct proof, and instead we do proof by contraposition, which is actually really, really easy. And that's really all there is on proof by contraposition. Thanks for watching.